So, yesterday we were looking at the members subjected to tension. So, you can see here as I emphasized yesterday, the difference between LRFD and ASD does not exist. If you use a 1.5 as a load factor divided by 0.9, which is basically the material factor coming from here. So, because the PD is at the bottom, so 1.5 divided by 0.9 will also become 1.67. So, it is almost you will see that there is no big difference as long as the consistent values are used. So, here the capacity is taken basically as a tensile strength of the member, which is gross area, which is multiplied by the yield strength of the material Fy times the cross sectional area of a member. If it is a pipe section, you will use a circular area calculation, or if it is a I section, flange area plus the web area. The next, the rupture only will happening once you have bolted connections. For example, if a beam is connected. So, if I take a cross section across the bolted section, then you will be having a not total area, you will have a area where minus the bolt holes, and that will covered by rupture, which is basically the elongation of holes and then starting to break rather than the failure by yielding. So, that is why there is a slight difference of this factor 0.9 for yielding without any holes, whereas if there is a purposeful holes made and then the rupture is going to happen, then there is a reduced factor of 0.75. So, calculation for tension becomes very easier, because area times yield will give you the yield capacity. No other forms of failure is going to happen, because you imagine if you have a member in full tension, definitely neither the global buckling nor the local buckling is going to happen, because it is under tension. So, that makes calculation for tension is very simple. At the same time, if you go back to compression, you will do the same thing, only thing is the stress is not going to be limited to yield value, because you will not be able to reach yield unless this member is very strong, quite big, wall thickness is bigger enough to avoid all local failure. For example, local buckling, I think we did talk about during the tubular sections, the local buckling because of the D by T ratio, global buckling because of KL by R ratio. So, same thing is going to happen, plus you are going to have additional problem. What we saw yesterday is the torsional buckling because of the instability due to longer length or smaller section. So, these three needs to be checked, that is what you are seeing here. You have to verify whether the section is susceptible to any one of these failure. That means, you will not reach the yielding and you fail earlier by one of them, and you limit the stress to that much. That is basically the FCR, which is the buckling stress. It could be local, it could be global, or it could be lateral torsional buckling, and that is what we are going to see. Each one case we will just see what will be the limits and what are the parameters involved in. Once you find this FCR value, then you calculate the nominal strength, which is basically again multiplying area times the buckling stress, and divide by a factor of safety will give you the allowable strength, multiplied by the material factor will give you the design strength for LRFD and allowable stress. The format is almost similar, only additional things that we are trying to do here is basically the buckling failures due to insufficient section, or section is too long and boundary conditions are different. Again, the unity check is similar, gamma times the load divided by the design strength, or load divided by allowable strength, which is again the similar idea for the tension. So, the FCR only differs in terms of calculation. For pipe section, what we were having? We were having D by T ratio, we were having KL by R ratio, and you were looking at D by T ratio for basically bending strength, not for compressive. Always you are using KL by R for your allowable axial stress, but of course, D by T ratio have some influence, whereas here you are going to look at the flange is open flange, web is also partly stiffened connected to the flanges. So, what we are going to see whether the flange and web are they cylinder or they are non-cylinder. So, that means whether they are not adequately stiffened. You have few cases whether you can have non-cylinder or you can have cylinder, cylinder with stiffener, cylinder without stiffener. So, you will see that 3 or 4 cases which you will take into account the effect of that on the the buckling stress that will come out here, instead of Fy you are going to calculate this. So, buckling of compact members, basic idea is if the members are quite compact, that means there is no slenderness on that, then you can straight away calculate using this empirical formula. So, you can see here is not something very easy to remember, it is a empirical formula from test. So, they have conducted several tests. So, 0.658 raised to the power Fy by Fe. Fe is the Euler buckling stress. I think most of you will remember this formula, pi squared E by KL by R square, depending on the boundary condition. You know, this is K will change, whether it is a pin condition, fixed condition, cantilever. So, you calculate this buckling stress and then substitute into this formula to get the value of the FCR. Now, this FCR depends on the KL by R ratio like this. I think you might remember the formula that we introduced for tubular section. It is quite complicated to remember, is not it? It is a little bit of long form, whereas here it is quite simple. Straight away a factor multiplied by yield strength. This factor is basically the calculation involving Fe, and when the KL by R ratio is greater than this value, you will be using straight away 87% of Fe itself, not the Fy. So, that is the difference that you are trying to make. So, this will be a case governing by buckling, this will be case governing by almost close to yielding. So, that is exactly the idea. And this what I have written here is doubly symmetric sections, because these are the simplest cases. You will go into singly symmetric, you may go into unsymmetric cases, which are also part of the AAC, which I have not repeated here, but procedure is slightly longer, means the asymmetry will create different forms of equations, that is all the difference, but the procedure is the same. So, just to simplify, I have given the symmetric sections doubly symmetric, the flange is symmetric and the web is symmetric about the y axis. So, this is basically the flexural buckling, which we saw about it earlier. The torsional buckling, the formula is given a little bit different, basically what I explained yesterday regarding the load applied at the shear center, but at the same time when the length becomes longer, starts to rotate and create a torsional failure. That is why this is sometimes called a flexural torsional buckling or sometimes lateral torsional buckling, one and the same. So, you do not need to worry about. So, this that means even before a global buckling occurs, because global buckling is because of slenderness, which is basically KL by R value, K and L will represent the length of the member or represent the radius of gyration, which is corresponding to the section. So, KL by R will be a global buckling phenomena, whereas the flexural torsional buckling almost is a mixed boundary condition, basically global as well as the local flange effects is going to affect. The larger the flange is going to fail early. So, that formula is also a empirical formula. So, you can see it is a derived form from Euler buckling, plus the effects of torsion is taken into account. So, pi squared E, Cw is the warping constant depending on type of section, and Kz will be with respect to torsional effect, not with respect to bending about x or y. I think I have given you this axis here, x and y is perpendicular to the axis of the member. So, the z axis will be along the member length. So, you need to find out how they are restrained. So, unless you have restriction, like yesterday I saw some pictures, something like this, if you have restriction of the member about rotation, then you can specify that length instead of the full length. So, basically this formula will involve Kz times L, and then here you have anyway conventional Ix and Iy. I think you might remember you know, in your applied mechanics calculation of polar moment of inertia, calculation of x and y, so about the principal axis, and then you can find out the polar moment of inertia, or if it is a simple section it is easy, otherwise you find x and y and then convert into the polar moment of inertia. So, all these values are known for the particular section. So, Ix, Iy, K, Kz and modulus of elasticity is known, then you can calculate back the shear modulus by simple relationship from elastic theory. So, you can calculate that also, or you can rewrite this equation in terms of E, just simply put E divided by to 1 plus mu, I think. So, you can calculate that also. So, either you will govern by this or govern by this, you have to find out which is the value smaller and then calculate. Now, singly symmetric, the difference between the doubly symmetric and singly symmetric is basically the flange is going to be different, top flange and bottom flange may be smaller, bigger. Many situations you will get into this type of in ship hull construction you will get very often this. You will have a ship hull plate, whereas the stiffeners will be T sections. So, when you want to take a equivalent section, you will always find that the stiffener will be thicker and the shell plate will be smaller. So, when you find out equivalent cross section, you will form something like this. Most of the hull bulkheads will be like this, but when you are doing building construction, maybe not this type, because we always prefer symmetric sections with runner beam. On top of it you will put the deck plate, whereas the ship construction we do not do this, like you will have a hull plate and just stiffen by T sections. Sometimes angle bars are similar sections. So, in that case the idea is similar, whatever we were looking at, only difference is you see the formula is getting slightly complicated because of the asymmetry of the sections. So, Fe will be calculated using this formula, and corresponding values of Fex, Fez, Fey and Fez is to be calculated using this formula. So, you can see here slightly complicated. So, imagine if you have a doubly asymmetric section, so it will become even difficult, and basically those are channels and angle bars or fabricated sections. You will see that these are only just matter of doing calculations, but the procedure is similar to. So, the values will be replaced by the complicated formulas rather than the procedure is not changing. So, doubly symmetric or singly symmetric, only the values needs to be calculated using corresponding formulas. So, in here I just explain Kx, Ky, as you know very well, is a flexural buckling about x and y axis like Euler buckling, and Rx, Ry is a radius of gyration. X naught, y naught is the shear center. For symmetric sections, at least one single symmetry, it will be along the web line. If it is doubly symmetric, doubly asymmetric, then you have to calculate the shear center using the shear flow theory, which will be slightly difficult, but for this type of sections, shear center will be the centroid of the section. Now, whatever we saw, basically buckling of compact members, no cylinder elements. That means you classify, you saw one table here, just go back here for clarity. Member classification for compression elements, we had flange, we had web, that means non-cylinder. We were all looking at, you look at the web and look at the flange, find out the thickness to width ratio or width to thickness ratio. As long as they fall within this category, they are non-cylinder elements, which is basically a compact. That is what we were looking at just now. That is why the subclass A is for buckling of compact or non-cylinder. I would put rather non-cylinder. Then if you look at the cylinder elements, what we are trying to do is follow exactly the same procedure, but because of its cylinderness, we want to have a reduction factor, which is basically a factor called Q. It must be less than 1, because that is what I was trying to emphasize early as first few classes. When you are designing structures, it is not that because you are intelligent you want to reduce the thicknesses, but you are going to pay the price somewhere else. As long as you make them slender, thinner, trying to reduce weight, that is what the idea, no? But then allowable stress will come drastically down. Either you increase the KL by R ratio or increase the D by T ratio, means it is going to become slender, and then allowable stress will be drastically reduced, which is not a good idea, because ultimately we were trying to reduce, but then allowable stress reduces, then you will go back and then make it bigger. So, that means as long as you keep reasonable D by T ratio, KL by R ratio, in here width to thickness ratio. For example, when you fix a flange within the limits of compactness, you will get full allowable stress. Once you make cylinder, automatically the allowable stress is going to come down. That is what the idea. So, the Q value is to account for the cylinderness of the flange and the web. So, that is the idea behind. Again, you will have a similar cylinderness bifurcation, KL by R less than 4.7 times E by Fy and then greater than. So, when it is greater, when the buckling is governing, the slenderness does not come into picture, but the slenderness do come into picture here, basically multiplied by q and also on the superscript of the 0.658. So, how do we calculate the q is a simple matter. So, q will be a multiplication of two components, one is qs and qa. Now, you can see here when you select I beam, you have two things can happen. The flange can be compact, web may be slender, or web may be compact, the flange may be. So, that means there could be a mixture of compact non-compact elements. It is not that both of them, if it becomes both of them compact, then no problem, because the multiplication becomes just 1. So, that is the idea behind. So, you can have, suppose if you have a fabricated gutter, many times we do this, you have flange and then maybe 3 or 4 webs. In many cases we use in offshore construction, because restriction of depth will be given to you. It is not that you can infinitely increase the depth to increase the amount of inertia. So, in such cases you will have many webs. In cases of very heavy shear force coming, webs will be able to take it. So, you may put more than one web. So, in here 1 is for members with no cylinder elements, qs multiplied by qa for members with cylinder elements, qs and qa for stiffened and unstiffened. So, basically you will calculate separately, qs for members with the elements unstiffened, qa for members only stiffened. So, you have cylinder, but stiffened, but still you will not be able to achieve 100%, because there could be a reduction. So, these values needs to be calculated. Again they are empirical formulas given for that, I think it is coming here, but before that you can see the relationship between KL by R ratio, which depicts this equation, basically this equation, the relationship between allowable stress, which is what basically FCR by tau, and basically in terms of megapascal, this is your KSI value, horizontal axis is your KL by R. Remember, we were having a similar graph for tubular sections, almost similar parabolic type of. So, you can see here, as long as you keep less than 100 KL by R ratio, somewhere around here you will reach typically about 100 megapascal, and if you have a KL by R ratio larger than that, drastic reduction in the the allowable stress, which is not very good. And that is why most of the codes they specify KL by R ratio needs to be restricted to 120, only very rare cases we go beyond, and you have to limit that. And in case of some of the big structures, we even restrict to KL by R ratio less than 100, especially primary structures. So, QS, there is a formula wherever you have Bf by 2 Tf less than 0.56 E by Fy, then the value of Q for unstiffened elements is 1. That means it is already compact. So, if you go back to the compactness table, let us just quickly go back, just in here, that is the value that we are looking at. As long as you keep less than 0.56, then your value becomes just 1. So, no reduction in the allowable stress. So, if you are between this and this, then there is a reduction factor, and then the cylinder stiffened. So, basically that is what we are going to see. So, and then between 0.56 and 1.03, the values of E by Fy is constant anyway, which is going to produce around 28, depending on what is the yield strength of the material, and the QS value takes this kind of form, is an empirical form. So, you got to be careful, but what has happened in the recent days, comparing the previous edition of IAAC manual from 9th edition to 13th edition, one good thing has happened is all of them has become non-dimensional. It does not matter whether you are using metric units or you are using English units. The earlier version of the course are highly dependent on the units. You have to use only the English units, convert back all the values to your metric units, though you are using design using the metric units or Newton SI units. All those equations in the older codes, 9th edition before, everything you have to follow the American units, otherwise these numbers are all corresponding to such type of units. So, because of the difficulties faced by the designers, now they have come up with modified form, everything has been non-dimensionalized. see here Fy by E is just does not matter, as long as you use consistent units. Do not go and use one unit for one and the other for different, then it becomes a problem. So, as long as you use consistent units, so you do not have a problem, B, T get cancelled. As you can see here, B by 2 Tf greater than 1.03, then the value becomes another form. So, Q values have to be calculated as long as you have cylinder elements, especially the flange, and they are not stiffened, that means left as such. Similarly, before seeing this, for cylinder elements, but they are stiffened, you could see here, as long as you have such elements with some stiffening. For example, many times what happens is we want to make the girder very deep, because we want to get more moment of inertia, thinking that by simply shifting the flange away, I will get more moment of inertia. That will be correct, provided you have sufficient thickness for your web, otherwise the web will become cylinder. So, even before you achieve the moment of inertia, it is going to be fail by local buckling of the web itself. So, what we normally do is we do that, and then also go and provide the intermediate stiffness to stiffen the web itself. So, it is not coming free by simply making the web height higher and higher, you are not getting free moment of inertia, you are going to spend more steel on stiffening them, so that the buckling does not govern the design. So, basically here QA is defined as the area of the summation of effective area of cross section based on the reduced effective width. So, whatever the width that you have originally provided, because it is becoming cylinder. So, you reduce the width, you calculate using this formula, and the gross cross sectional area of the member, which is basically the summation of the web and the flange. So, that is the ratio that you are going to get, as long as you have this reduction smaller, the QA value will become 1, means it is close to the full area. As long as the reduction value is larger, then you will have less value of QA, which will correspondingly reduce your allowable stress. Both of them I have just got the graph how it varies. As long as the cylinderness increases, you can see here the value from 1 drastically reduces. So, that is one for the unstiffened elements. Similarly, for stiffened elements, you can see here just for one particular value I have plotted, it is 1 for up to cylinderness of about 11, 12, after that starts to reduce drastically below 0.5. So, which is not very good. So, ultimately you have 0.5 times 0.5, it will become very small allowable stress. So, as well go back and then instead of putting lot of stiffening, you make the section less than the value of cylinder. So, that is the idea behind. So, if you go back here, for cylinder elements, we do have a provision that you calculate the reduction factor in terms of stiffened element and unstiffened element. The next one what we want to look at is the bending. So, we have looked at tension, we have looked at compression, both of them involves the area, cross sectional area, and the yield strength or buckling strength. Buckling strength is governed by KL by R, KL by R plus the stiffened, unstiffened, basically the compactness of the members and the flanges and web. The next one we are going to look at is the major axis bending. I think for pipe sections we did not talk about major axis, minor axis. It is a circular section which uniform property all around, principal axis is same x, whereas here we do have a problem because it is not uniform throughout, and basically the horizontal axis we normally notation given as xx yy does not matter, and basically the major axis bending. The vertical axis is the minor axis. As you can see, when you calculate the property itself, you will find the flanges are kept away. So, you will get a higher moment of inertia. So, you can give a notation as major axis bending, and predominantly these beams are placed for floor beams in this fashion, nobody go and turn the. So, major axis bending and minor axis bending, what is the difference? Suppose if you go and put one flange or one more web on this sides, then they become actually does not matter whether this is major axis, that is minor axis, it becomes almost similar. but most of the idea behind which we were talking about yesterday, we wanted to increase the bending. One plane large bending is there, the other plane bending is not there. Horizontal bending for deck structures is very small, maybe a very little. So that is why you maximize the bending, and what we are worried about is the major axis strength. So if you look at here, again similar idea, allowable flexural strength and design strength. This is for LRFT, this is for the allowable stress design, and the nominal strength is given by yield strength multiplied by the modulus of the section. So this is where one major difference has been made. As long as you look at IS 800 or any other codes, including the 9th edition of ASE codes, this has always been elastic section modulus, but in the recent times a lot of studies shows that in the form of yielding it takes higher strength than actually elastic, and that is where you see this plastic section. As long as the section is governed by yielding, you can go up to plastic section modulus, that means you are having higher strength. So by making the members compact, this is what you are going to achieve. You are going to get higher strength than what you are going to get when you make it slender or non compact. Now you see here, yield strength multiplied by the section modulus will give you the nominal moment capacity, which is basically the one that we are looking at, divided by a factor of safety will give you allowable moment strength, and multiplied by the material factor will give you the design moment capacity, and the unity check is exactly same as what we were looking at, gamma times m. M is the applied moment external forces divided by design moment or the design capacity, and similarly for allowable stress design, m divided by. So you see here the material factor is 0.9, and basically the allowable stress factor, which is 1.67, it's almost same. Now the matter is, how do we find out this Mn? If yielding is governing, which is the first one, very simple, because Fy multiplied by section modulus. Section modulus calculation simply using plastic theory, which we learned about the other day, you can calculate. If it is a complicated shape, it may take little bit more time, but if it is a pipe, which is very easy to derive, I section which is symmetric, which I have given you I think in the previous slides. So that is not a problem. So it can be governed by yielding, which is easy, or if it is governed by torsional buckling, then we are going to look at what is the value of this Fy will be replaced by buckling stress. That is exactly the difference. So what we are looking at is the torsional buckling may govern as long as either the section is smaller compared to the length, is a relative, it is not just absolute. You can have longer length as long as the section is bigger, it is not going to have torsional buckling. So that is where you will see that the section property will come into picture, and the length of the member from support point to the point where it is restricted from torsional buckling, that means rotation is prevented. So you have three cases. One is basically the length of the compression flange restricted against rotation, which is called LB. So the definition of LB, I have already shown one picture. The length of the member is full from support to support, but middle we have got one lateral member which is preventing the member from rotation, which is basically the LB. So if LB is less than the LP, which is going to be calculated using some empirical formula in the next page, as long as you keep your length of that unsupported compression flange, then you do not have torsional buckling happening. That means if the flange is restricted, then it is good. That will be the case most of the deck structures in offshore we will have, because you put one big deck plate, like you have a floor plate, and weld the floor plate to the beams. So what will happen? The floor plate will not allow the beams to rotate. So most of the cases you will see that this will be very small. Where it will be bigger? In case where you have open sections, there is no floor, but maybe there may be a open grating, the open deck floor, then you will have such kind of problems. Then you have two cases, LB is between LP and LR, and LB is greater than LR, basically the relative term. This is a moderate case, this is the extreme case. So, basically these two cases we will calculate the, instead of Fy multiplying by Fy here, you will be replacing that Fy with this value of calculated stresses. So, basically in this here, this whole term is replaced by this, whereas in the case this last one LB greater than LR, you see here FCR multiplied by elastic section modulus, that is the difference that you find. So, you go back here, you have full yield stress multiplied by plastic modulus, which is going to give you a very large moment capacity. When you made the section very small, or when you made the member longer, you see here the moment capacity is reduced by almost, you are reducing by 30% here, and the last case when it is becoming too large, then you actually go into buckling, and also you have the modulus replaced by plastic to elastic. You will see that for I sections, I think we remember what is the ratio of plastic to elastic, somewhere around 1.2 to 1.3 or 1.15 depending on. So, another 10 to 20% reduction. So, you can see here allowing torsional buckling to happen, not a good idea, you know, it is just going to reduce it. And again you will see a large formulas for, but again the form of the formula is very similar to Euler buckling. You can see here only the additional term is added on the right hand side, which is empirical, just to fit the you know, the test results. So, FCR is calculated using pi squared E, and here you see slightly different form of LB, because it is not anymore a KL by R, it is basically the torsion prevention by means of lateral compression restriction. And the LP values and LR values which are used here, you see here LP and LR are again calculated using this big formula. These formulas used to be very simple before the 13th edition, because it was based on KSI units, but when they try to do non-dimensionalization, these formulas have become quite big, very hard to remember, but does not matter. So, you can use the codes to refer most of the time, because memorizing this is no use. So, the LP values and LR values are the limit values where the bifurcation takes place from this equation to the equation for calculation of Mn. A typical graph which describe what we were talking about, the slenderness versus you know, the nominal flexural strength, which is basically the moment capacity of the section. So, you can see here, as long as you keep the flange compact, which is basically this is the compactness parameter, which is B divided by 2 Tf, because total flange divided by half divided by the thickness will give you the compactness of the cantilever section of the flange one side, which is, this will be around 9.2. So, as long as you keep it less than 10, you could see here it becomes compact flange, you achieve full capacity, which is Fy times the plastic modulus. And then in the transition region, basically you get a reduction of about 70%. This is described by the second formula, this formula basically. The last one, which is basically here, will reduce less than 50%, which is not very good, having the section and make the flange bigger just because we wanted to be increasing the moment of inertia, but just you can increase the moment of inertia, but then the allowable stress decrease, not a very good idea. So, that is why most of the time when we design, we try to keep it within this limit if possible. If it is not possible and you want to still, then go for between, but never ever come into cylinder flange, because the section will not be able to achieve that capacity. So, that gives you an idea of how the variation of the moment capacity with respect to compactness of flange. Most of the predefined sections described by codes, whether it is American code or Indian codes, mostly they make it compact flange, and you do not need to really worry, even if you check it will be compact. Only fabricated girders or fabricated beams which we are making from plates, you will have to verify that. This basically the relationship between the unbraced length with respect to flexural strength. So, you see here the Mn, and where we are is basically the elastic torsional buckling, almost somewhere between here to here, the equation that what we are seeing. The inelastic and the plastic capacity, this is only used for plastic capacity design, where we use for the accidental cases. So, it is exactly opposite. So, most of the cases will be using in this form. The value of CB, which has been appearing in many of the equations, you will see here CB here, is depending on the moment distribution across the member, very similar to the values of CM, which we talked about during the design of tubular members, is depending on the basically the distribution or the profile of the moment along the member length. The typical case, I have just given you an idea how the moment variation, A, B, C, and the maximum moment, absolute maximum, and then the moment at the locations A, B, C. Basically, A is 1/4, middle, and the 3/4, and will give you an idea of the reduction factor for the torsional buckling, which is CM. We were talking about the flexural buckling in tubular members. In here, it is CB, and you calculate and apply this value to reduce the buckling. Similar procedure can be followed. I have just described. Also, I have just given you the reference number, in case if some of the parameters are missing, you can go back, because there is almost 8 or 9 cases, starting from compact web, compact flange, all the way up to the cylinder web and cylinder flange. I have picked up 3 cases for this presentation basically, and this number represents is the section number in the ASC code. So that you do not get confused. In fact, sometimes you get confused. So basically, this one doubly symmetric, compact web, non-compact flange. What we saw just now, compact web, compact flange. That is what we saw just basically one of the case. So when you go to doubly symmetric, again compact web, but non-compact flange. The flange is going into the transition region, and you will see a similar approach, only the formulas will be different, and you will need to calculate the nominal moment capacity Mn, go back to your design equation, substitute. Then the next one is, so in this basically need to highlight the difference for compact web, and when the flange becomes non-compact, the equation is replaced only for Mn, and remaining is almost same. For doubly symmetric, compact web, but the cylinder flange. So web is kept compact, but the flange is coming from compact, non-compact, and becomes cylinder. So cylinder, you could see the form of equation takes place here, it becomes elastic, there is no more plastic section model is going to come. So it becomes reduced capacity, you will be in the tail section of the you will be somewhere here. So what we did was, we did here and then in here. The last one is basically just a typical case where plate girders are going to be designed. Most of the time when we design plate girders, we want to make the web very big. That is what the thing immediately we come to our mind. We will make the depth of the section so large to increase the moment of inertia. So the web becomes cylinder, and once the web becomes cylinder, it becomes almost capacity reduction is very drastic. So that is where you will see doubly symmetric, but web is cylinder. Once the web becomes cylinder, it does not matter whether you have compact flange or non-compact flange or cylinder flange, because the capacity is going to be governed by the web buckling itself. So that is why it does not matter whether you have the flange in which category. So it is automatically governed by the web buckling, and you have to check all these 3: lateral torsional buckling, compression flange local buckling, and then tension flange yielding, and the formulas are almost similar. You see here, in case of yielding for compact web, compact flange, Fy multiplied by plastic modulus we had. So once the web becomes cylinder, you see here there is a multiplication factor, which is basically its notation is plate girder notation, RPG, and multiplied by Fy, but then it is not anymore a plastic section modulus, it is a elastic section modulus of the section. So we need to just follow wherever the multiplication factors you have to calculate. So, if it is yielding is Fy, if it is buckling it is FCR, just the equations are getting replaced because the web has become slender. And again for torsional buckling you will have a 3 classes, bit less than LP and between LP and LR and then greater than LR. The formulas are instead of 0.7 it becomes 0.3 because the web itself has become slender. Otherwise if you look at the form of the equation is exactly same. So, the reduction is even further, and then here the buckling is similar equation what we are seeing Euler buckling, pi squared E divided by L by R square multiplied by CB factor, which is very similar to the previous case where we were computing by bending moment distribution. And then the values of LP and LR repeated again, and the parameter for reducing the bending strength because the web is cylinder is taking this kind of form. So, what is this parameter? Basically this parameter is to account for cylinder web of the girder, which is that is why it is basically the PG. Most of the time this is applicable for plate girder. In fact, if you have seen the ASC code previously, there was a separate section for plate girder design, even in IS 800 you will see, but now the new code there is no separate section for plate girder because they have merged the section together and they have made several cases. One of the cases is a plate girder design where plate girder means the web depth is made very large. So, that is the idea behind. There is no separate or exclusive section for design of plate girders as such. This is the only parameter that will be differing from when it is a short girder or a long depth plate girder. So, you just have a multiplication factor. Now, if you look at this parameter AW is the ratio of the compression flange part of the web and the compression flange 2 times the compression web side divided by the compression flange, that is the AW, and H is the full depth, H naught is the centroid of the flanges basically between center. The H is the distance from neutral axis to the compression flange, you multiply by 2, just a definition. RT is the radius of gyration. So, basically you will substitute these parameters just to see because whether the compression side of the web is buckling or not. That is why you see here the RPG always will be less than, if you get more than 1 something must be wrong. And then you have compression flange local buckling, because you see here 3 things needs to be checked. One is the lateral torsional buckling and then the compression flange local buckling, because the web itself is trying to bend and you also have tension flange yielding. So, similar to the previous case exactly, except this will be 0.7 change to 0.3, and again RPG is the same value, and you will calculate the section modulus corresponding to the compression flange only. And then for 3 cases you have compact flange, non-compact flange and cylinder flange. Cylinder flange is similar to the last formula what we saw, and then the yielding case you will see that Fy multiplied by elastic modulus. So, the difference between last time we were seeing only Sx, I think most of you first 3 cases. So, here you have 2 different cases, compression side and tension side. If you have asymmetric basically the flanges, hope you remember you can calculate the neutral axis from bottom, which will be your compression side or tension side depending on the bending, and calculate the top side and divide by corresponding neutral axis distances will give you the Sxc or Sxt. If it is a symmetric section, both will become equal. So, the minor axis bending, so what we saw was all the time it is bending just along the major dimension. So, also can bend in the horizontal direction if you have the load perpendicular to the web of the section, basically from the lateral. So, the only load that we will get from our offshore or anywhere for that matter will be the wind loading, which is going to be predominantly smaller, it is not going to be very big load. But the second thing what can also happen, not only direct loading on the member, but also loading elsewhere can make the beam to bend horizontally. It is not that the beam is going to bend only purely on the loading on the member itself. So, sometime it may happen, and but very small loading. So, that goes hands in hands with our idea because we have made it very weak. If you look at the moment of inertia calculation of an I section, it will be drastically smaller compared to the major axis bending, which is good. So, the idea behind here is very simple. I shaped members and channels bent about minor axis, your yielding can govern, basically jet y is taken. That means, the buckling is not going to happen here, because there is no such phenomena, because there is no two flanges. For example, if you keep the I beam turned 90 degree, then buckling will come, whereas here when you keep the section primary section loaded in the perpendicular direction, the lateral direction there is no buckling, because there is only one web is there, there is nobody else. So, unless you have two flanges or two webs, if you make a box section, then buckling will come, but here there is no such thing. That is why you still go back to a very good capacity, but of course, jet y if you calculate for such a section it will be very small. So, yielding is f y times jet y, but limited to 1.6 times the f y times s y. So, you can see here the ratio between jet y and s y matters a lot. As long as you keep the ratio larger, then it is good, but unfortunately for I sections the ratio is about 20%. So, you will still see a reduction there. So, for local buckling, compact flanges, you do not need to change anything, that means buckling does not apply. When you have sections of non-compact or cylinder, you apply these formulas, very similar to what we did for the major axis bending. So, you can see here minor axis bending, one great advantage is the lateral torsional buckling is not going to happen, because you have only one web. Otherwise, only because of this compactness of the flange, if it is compact or cylinder, you apply the reductions. Basically, when it becomes cylinder, you take the buckling capacity based on this formula, which is very similar formula to our major axis bending. So, in summary, what we have done is tension, compression, and basically the major and minor axis bending. Major axis bending 4 classes: compact web, compact flange, and then we had compact web, non-compact flange, compact web, cylinder flange, and then cylinder web with compact, non-compact or cylinder flanges. So, all the cases for doubly symmetric section we have seen. So, you can have singly symmetric sections, you can also have doubly asymmetric sections, or you can also have built up sections. So, you can see each one, what you need to understand is the form of equation. Compactness affects KL by R affects the allowable compressive stress, whereas the compactness allows the bending strength to be drastically reduced. So, we will see shear tomorrow and followed by I think few examples.